Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy at Foothill College in Silicon Valley, and it's my pleasure to welcome everyone to this lecture in 2022 in the Silicon Valley Astronomy Lecture Series. These programs, which go out to the whole world on YouTube and in podcast form, are sponsored by four wonderful organizations: the Foothill College Science, Technology, Engineering, and Math Division, the SETI, or Search for Extraterrestrial Intelligence Institute, the Astronomical Society of the Pacific, which has been connecting astronomers and the public since 1889, and the University of California Observatories, which includes not only their big modern observatories in Hawaii and elsewhere, but also the Lick Observatory in San Jose, which is the oldest continuously operating mountaintop observatory in the world. And we're delighted to have the support of all these organizations. We're going to have a talk tonight, and we encourage you to ask questions by sending an email to an email address that will appear on the screen for you as well: astronomy@foothill.edu. Again, that's astronomy@foothill.edu. So without further ado, it's now my pleasure to introduce our speaker for tonight. Dr. Michelle Thaler is an astrophysicist with over 2 decades of science communication experience. Her research involves the life cycles of stars, and she's worked at the Jet Propulsion Laboratory in Southern California, NASA headquarters, and now at the Goddard Space Flight Center near Washington, D.C., where she's currently the liaison between the Office of Communication and the Science Directorate. Outside her work at NASA, she has appeared in many television science programs, and you've probably seen her in such programs as How the Universe Works and Space's Deepest Secrets. She's done 2 TEDx talks about astronomy and has hosted the podcast Orbital Path on public radio. More recently, she is the lead professor in a new astronomy course in the Outlier sequence of online courses. So we are delighted to welcome her. It's been way too long since we've heard from her, and she's going to be talking about living with a star and the issue of habitability in our universe. Ladies and gentlemen, it's an honor for me to introduce Dr. Michelle Thaler.
Oh, that's wonderful. It is so good to be here. And Andrew, please, right back at you. You are one of my idols in astronomy, an incredible educator yourself, and an amazing ambassador for astronomy. And I am just really thrilled to be here. I'm sorry that this is virtual. Hopefully sometime this year I'll be out to see people in person again. But so as Andrew was saying, I'm an astronomer at Goddard Space Flight Center. Right now, this is the largest of NASA's bases. There's about 10,000 people that work at Goddard. We've all been working from home since about 2 years now, which is just amazing to think about. So I'm wondering if we'll ever get back that sort of collegial atmosphere of all of those seminars and everybody talking in the cafeteria and all of that. It'd be interesting to see. So tonight we're going to talk about something that draws in so many different parts of astronomy, a bit of biology, a bit of geology, talking about what makes a planet habitable. And a lot of this relates to how our star works, the sun, and how the different stars in the sky have their own planetary systems as well. So because there's some stuff that's literally hot off the presses, I have some images to show you today that actually were published today by NASA. So we'll talk a bit about that and some of these things. This is right up to date. I've spent the last, I would say, 6 months getting ready for the James Webb Space Telescope launch. And then I spent the last 2 weeks recovering from it. And so now I'm ready to talk some astronomy again. So let me go ahead and share my screen, and I will start my presentation. So hold on just a sec. All right. Okay. So what you should see, hopefully you can still see me in the corner there. This is a beautiful picture from the Hubble Space Telescope of probably my favorite object to look at in the southern sky, which is the Carina Nebula. And when we talk about habitability, I want to start really from scratch. We're going to talk about the building blocks of life, how you get them onto planets, what makes that planet sustainable, how that can actually keep life going. And we're going to look at this in sort of a broad context about the whole evolution of a planet. Now, you and I and everything on Earth, I mean, we only have one example of life, the life here. And everything on Earth uses organic molecules, which means molecules based on the atom of carbon. The element carbon sort of forms the skeleton of all of the chemistry that makes us up. That's what the word organic means. And the other thing we know that all life uses to some degree is water. And liquid water is necessary even in tiny, tiny amounts for any life on Earth. So let's start by looking at where these building blocks of life come from and how they get to a planet. Now, in this image, the Carina Nebula is this wonderful maelstrom. I mean, the image that you're looking at here is actually a couple light years across. And there are new stars being born. You see a cluster of sort of pink, beautiful scattered jewels in the middle there. Those are all young, hot stars. It turns out that as stars evolve, specifically dying stars are just very, very good at making the element carbon. It's one of the most common elements made naturally from the evolution of stars. And carbon is a very sticky atom. Again, just the natural innate the innate characteristic of carbon is that carbon wants to form bonds with other carbon atoms. And pretty soon you start sticking carbon together and you get organic molecules, the molecules that make us up. So this is actually the true origin, the building blocks of life come from these huge clouds where stars are forming and dying. And as they die, enriching the cloud with the element carbon. Like I said, dead stars are great at making carbon. So how can we get some samples of what our chemistry was like really before life began? And it turns out that they are literally falling out of the sky. Meteorites are really wonderful things because meteorites are basically small chunks of asteroids. Asteroids are rocks in our solar system that usually are very ancient. They probably formed right when the planets were forming in our solar system, but they never got built into larger bodies. You see, the entire evolution of a star and the solar system around it really just runs on gravity. There is gravity that brings together all of this dust and gas from space, from these clouds. As it compresses down in the middle of a cloud, it can actually, if you press a gas together really hard, you'll raise its temperature. And when you have that much hydrogen and dust around, you actually can raise the temperature in the cores of these clouds to millions of degrees, which will ignite a nuclear fusion reaction and a star will turn on. But the cloud around it, is basically whatever's left around that forming young star will form planets. And again, by gravity pulling things together. But in some cases, some things get left out. They don't ever get made into bigger objects. And that's why asteroids are so interesting to us. Now, what you have here is a picture of a laboratory that is literally 2 stories below my office. I often go down here just to kind of feel like a scientist. And it has our astrobiology team at Goddard. And the people here are sort of some of the leaders of that team. Over on the left-hand side was the official photograph that they took of them. In that little vial, they have a sample actually of a comet's tail. NASA, quite a while ago now, actually flew a probe through the tail of a comet. And as it actually sampled what chemistry was in that, it brought back a small sample to Earth. Jason in the middle there, Jason Dworkin has it in his hand, some of it. And it turns out that the amazing thing is that some of the basic building blocks of our proteins, amino acids, were present in that comet tail. And in meteorites, you get even more. Some meteorites are very rich in carbon, organic molecules. And some meteorites are actually more complex than my own body. I have a carbon-rich meteorite here that's actually in my own collection called a carbonaceous chondrite. And there's actually more different types of organic chemistry in here than in me. I actually use fewer types of molecules that are in this little slice of meteorite. And the reason it's called a chondrite, I got to show you because it's just so cool. If you'll notice, there's a little gray dot kind of in the middle of that little slice I have here. That's called a chondrite. And we think that this was actually sort of the first solid material in the solar system. This little droplet was once a tiny little kind of liquid droplet. And it got stuck inside this meteorite that formed around it, this sort of asteroid that got ground up and in space. And we think that probably this was the seed of a planet. This was some of the first material that began to come together and gravitationally bring stuff more and more together. But this one never got made into a larger planet. So I've got my little baby planet there. So carbon-rich material is present. Now we just need to bring it down to Earth. And it turns out that meteorites and comets are very, very rich with that. So that's really where we come from. We think most of our chemistry came from these objects that fell down to Earth over time. In order to get a better sense of what that chemistry is like, we actually just in the last, it was a year ago in October, we sampled a comet and we now have a very large bit of this wonderful, pristine material. It's basically unchanged for the last 4.5 billion years. This is the OSIRIS-REx spacecraft. This is an artist's conception of it. And this small spacecraft went out to an asteroid called Bennu. And by the way, I should say this was during the height of the pandemic. It was October a year ago. It was before we had a vaccine. This was the first time I ventured out of the house. I got on a plane to go to Colorado to actually be present and do some of the media work for this amazing mission. But as you see from this illustration, OSIRIS-REx has a long arm that was meant to go down to the surface of the asteroid and basically suck up material. And then that material will be brought back to Earth in 2023, next year. So I have a couple little fun videos to show you. This was really quite an amazing thing to do because the asteroid Bennu turned out to be a lot more jagged and rocky and mountainous than we expected. So we needed to come down very, very easily between some of these really big boulders and finally get through and actually get one of these samples. So this is the footage of the night and what was going on. And you're going to see the people's reaction in this mission control. And then the footage that you'll see is actually real footage taken by cameras on this little spacecraft. So I'm going to play that video. Sure. Did that do it? Oh, there we go. So there you have it. So I was there during that wonderful time. It was incredibly exciting. And then we all thought that we would go home and just have a bit of a rest. And in a couple of days, we tried to sort of spin the spacecraft around and measure the mass of the sample that we took. And the original plan was that if we wanted more sample, we might go down and actually try another one of these sort of suction events, suctioning up the asteroid dust. But what happened is this is actually a real image from the cameras on OSIRIS-REx. We turned our cameras towards that little suction head, and we noticed there was actually stuff flying out of it. And it turned out that we had been overly successful. We had sucked up so much material from the asteroid that we'd actually jammed this thing open. And so we were actually losing bits of our sample over time. And so all of our plans were changed, and immediately this head was actually put into a capsule to get ready to send back to Earth. And this is an animated images of that happening. There you see the capsule in there and the sample head. And this will be returning to Earth, like I said, in 2023. And we'll be picking it up in the desert of Utah. And hopefully when that happens, we'll have a kilogram or more of this really pristine material from the solar system. And the reason these things are interesting to us is that it shows us what our chemistry was like before life, before billions of years of evolution happened. So this is an amazing chance to actually sample our history from billions of years ago. So we know where the chemistry of life comes from. And now the other big question is water. And, the Earth, of course, has, all of the oceans and all the fresh water that we use. A really interesting thing is that we have some question as to how much water was here at the very beginning of the planet. And we have some reasons to wonder how much water was on the Earth. We now can observe other planetary systems forming in space. And one of the things we've noticed is that when you're as close to a star as the Earth is, the heat and the radiation, and also what we call the solar wind. The solar wind is a wind of particles. It's not a wind through air like we think of on Earth, but it's actually a stream of particles, mainly small particles like protons or the nuclei of helium atoms, some electrons. But these tiny particles get accelerated off the sun, and they create a wind that actually blows things through the solar system. The solar wind actually is strong enough that we need to accommodate for it on some of our spacecraft. Even the James Webb Space Telescope that just launched has some stabilizing parts to actually help if the solar wind blows it around a tiny little bit. So this is an artist's conception of what we think the formation of a young solar system looks like. And in the very heart, you see a young star there beginning to shine. And then everything around that star that's glowing kind of yellow, and orange, those are areas where the inner planets are forming, where Mercury, Venus, Earth, and Mars would have formed. Farther away, the solar wind blows out the lighter material, like water vapor. And that material is blown out until it's finally cold enough, far enough away from that young star, that it condenses into ices, tiny little particles of ice. So when we look at planets and young solar systems forming, it really does appear like most of the water is in the outer reaches of the solar system. It's not where the Earth formed at all. So this is an artist's conception. I want to show you a real image. This is an image from an amazing telescope called ALMA, which is an array of, it's actually microwave. You can think of it almost sort of an array of radio telescopes in the Atacama Desert. ALMA is up at nearly 17,000 feet, 16,600 feet. And it's an incredibly powerful telescope. And it took this picture of a very young solar system. And you can see here that they've drawn in where the orbits of Neptune and Pluto would be in our solar system. So you get a sense of the scale. This is actually bigger than the orbit of Pluto. And they've put a white line that they call the snow line. And the snow line means the distance away from that young star that water is finally cool enough to condense into these particles of ice. And then those particles of ice can be made into icy planets, planets with a lot of water. But close into the star, things are pretty dry. So when we think about habitability, one of the things to think about is, where is that planet in the solar system? And if water requires life, and I'm not saying that all life everywhere must use water, but we know that the one instance we have of life working used it. It's kind of hard to get liquid water into the inner solar system. And this is some of the amazing parts about the complexity. We think of Earth as a water planet, but in fact, we're quite dry compared to other bodies in the solar system farther out. And in this diagram, it's one of my favorites. There's a little blue bubble near each of these objects, Earth, Europa, and Titan. And that bubble represents the volume of all of the water on that planet, if you actually could gather it up into one sort of bubble of water. So Earth's a big planet, but it actually has a very, very thin film of water on its surface. Europa and Titan are moons in the outer solar system. Europa is a moon of Jupiter, and Titan is a moon of Saturn. And Europa, we estimate, has about twice the amount of liquid water that Earth does, even though it's a smaller body. And Titan may have up to 4 times as much liquid water. And let me be clear about that. We're talking about liquid water. Both Europa and Titan are very cold worlds. They actually are very far out in the solar system around Jupiter and Saturn, but they have internal heat that actually allows them to have liquid water oceans underneath, in the case of Europa, icy shells. In the case of Titan, some more interesting methane-based rain and lakes. So it turns out the Earth doesn't really have that much water at all. Now, it may be, and this is something that we're studying as we look at bodies in the outer solar system, that the water in your body right now, most of the surface water on Earth, actually did come from the outer solar system. It didn't begin here. There almost certainly was some amount of water in the rocks of Earth, when Earth was forming around the sun originally. But on the surface, it could be that most of this water actually came in later, sort of extraterrestrial water, if you may. And we know that both comets and asteroids, and I've got pictures of both of them, but if I go back to my little asteroid slice here that I've got, asteroids contain quite a lot of water actually in the minerals themselves that make up the asteroids. There are actually even some asteroids, some meteorites that we have samples of, that have little inclusions, little tiny reservoirs of liquid water. And so how would you get liquid water from all the way out around the orbit of Saturn and Neptune and Pluto? How would you get that into the inner solar system? Well, one of the amazing things that we now know is that, this was something that we had no idea about 20 years ago, is that as planets are forming in the young solar system, they may actually move around quite a bit. They may actually come in towards the sun and then go back out into the outer solar system. And specifically, this is an artist's conception. of some planets that are forming. And as they form, you can see they're actually kind of sweeping up bits of this disk of debris. They're forming out of this disk of dust and gas around this young star. We never really thought before about the interaction between this disk, this thick disk of dust and gas, and the planets moving around. And so we now believe that specifically Jupiter, there's a lot of good evidence that Jupiter may actually have sort of pulled against this disk. The disk kind of slowed it down as it was going around the young sun. And it may have actually lost some orbital energy and gone in almost to where Mars is today. And then amazingly, what happened is that as the outer planets, Saturn, Uranus, and Neptune were forming, they eventually tugged Jupiter little by little back out. This is called the Grand Tack hypothesis. It's a great thing to read about. But one of the things we think now is that this may have helped actually deliver some of the water to the inner solar system. Now, I hate graphs, but I'm just gonna play this one. I'll play this on a loop. What you're looking at here is from a scientific paper about this. And what I want you to pay attention to is these circles that you see are the orbits of the outer planets. So we've got Jupiter, Saturn, Uranus, and Neptune. And all these green dots represent lots of asteroids and small planets that formed at the very edge of our solar system where water was plentiful. As these planets' orbits start tugging on each other, as the planets start moving each other around a little bit, there is a point where they basically say a catastrophe happens. All of these outer planets they're the very, very outskirts of our solar system get gravitationally disrupted. The gravity of these larger planets start to throw them all around the solar system. One thing we know from looking at the crater record on the moon, which is not very changed in its billion-year history, because there's nothing to erase craters. Like on Earth, you've got all of the erosion and plate tectonics and everything that changes our surface. The moon went through a period of intense bombardment right around when this model suggests Jupiter and Saturn would have been throwing these small planets, these small icy worlds around. So again, with habitability, it may be where in the solar system you are. And are there giant planets out there in the solar system that in the very early parts of the planets, they gravitationally destabilized and threw things in? There's more reasons to think this happens. The largest asteroid Ceres is a very strange asteroid. It's very rich in water. And some of these small moons as well in the inner solar system are basically more, I should say they're a bit wetter than they should be. So there's some really interesting ideas about how this catastrophe of throwing around all these small icy bodies might have brought water to us. And here's from this mission completely blew my mind. This is an image from the Rosetta mission from the European Space Agency. NASA contributed the cameras for this. And this is the amazing comet 67P. And this comet's about 8 kilometers from end to end, sort of shaped like a dumbbell. And we actually were able to land on this and sample the water in this particular comet. And it turns out that our water in our bodies and in our oceans is a little bit of a better match chemically to the water we find in asteroids. But I'm sure comets contributed some too. Because asteroids are such an important link to our past, where did our organic molecules, our chemistry of life, where did our water come from? Right now, we have a mission called Lucy that is on its way out to some very special asteroids. Jupiter, as you know, is a giant planet. It has more than 300 times the mass of the Earth. And Jupiter has trapped some asteroids in its gravitational orbit. It's called the Lagrange points. And it's trapped these asteroids there since the formation of the solar system. These asteroids may be very, very old, and they may have some clues as to what the evolution of our solar system was like, and maybe even this era where the planets might have been throwing things around. So the Lucy mission is already launched. It's on its way to Jupiter now, and I'm really looking forward to finding out what it discovers about these asteroids. Okay, so now we've got the building blocks of life, and now we've got water. The next thing I want to talk about are the conditions necessary to sustain life, to keep a planet habitable. And we'll start here in the inner solar system, and we'll move on to some other things too. But starting in the inner solar system, you have here 3 planets that are either habitable, were habitable in the past, or I would say are very, very near misses of being habitable. So Venus and Earth and Mars are presented to you. These are all actual images of the planet. As you can see, Venus and Earth are very close in size and mass, and we believe in composition as well. Mars is quite a bit smaller. A lot of people don't realize that Mars is quite a bit smaller by volume, and by mass, it's only about 1/10 the mass of Earth. So some of the things that will now influence whether a planet can stay habitable have to do with how active a planet is, how much mass it has, and what its atmosphere is doing. And a lot of these are going to go back to how we interact with the sun and with that solar wind of particles that I told you about. All right, so let's start the story. Searching for life on Mars is something that's been going on now for pretty much all my life. And one of the things we know now that we've been down to Mars with multiple rovers, we've surveyed the whole surface with our satellites, we know Mars used to be very wet. In the past, Mars had a climate very much like Earth. And amazingly, we believe the same is true of Venus. There's growing evidence that Venus once as well had surface liquid water, had a very nice, friendly atmosphere. But something happened to these planets over the billions of years of evolution in the solar system. And so, one of the reasons we explore our solar system is to understand our home better. It seems that planets really do have kind of a limit to their lifetime, a limit to how long they can be habitable. And one of the things that's a little bit sad is that in this case, I'm not talking about global warming. I'm talking about the natural cycles of the solar system. We believe that the Earth too will someday lose its habitability, probably because of the way the solar wind is interacting with us. And I'll sort of talk a bit about that more. But going on to the surface of Mars, there was a really incredible discovery that happened just, I believe it was last week or about 10 days ago, that came out of the Curiosity rover. And this is a selfie from Curiosity. This is a real picture of the rover on Mars. It has a wonderful camera on an arm, so it can actually take a selfie just like we would. When this landed, I still remember that night. I mean, that was one of the best nights of my life. This rover was pristinely white, perfectly clean. And as you can see, it's gotten kind of dirty and sort of sandy colored after it's nearly 10 years on Mars. But Curiosity has the ability to make small little drill holes into the surface of Mars and to analyze the soil and the air as well. But there was a pretty incredible discovery that happened just recently about the soil. So this is a close-up of a part of Mars that Curiosity was drilling a little while ago. And I have to say, this kind of makes me smile because this is called Vera Rubin Ridge. And Vera Rubin was a wonderful astronomer, a real pioneer woman in astronomy that I had the great fortune of knowing for a while. She's since passed away, but this was named in her honor. Now, if you notice closely, the rock looks like it has lots of different layers to it. And that's real. This actually was once the bed of an ancient lake. The lake had different levels of water that came up and down. It left different layers in the soil. And then there's also been wind as well to deposit these layers back and forth. So Curiosity was drilling, and this is a site of the actual drill hole. This is the real one. This is a picture of it. Curiosity was drilling in some of the rocks around there, and it found a chemical signal that if it were on Earth, we would say is due to life. It found probably the best, most intriguing clue that perhaps life did exist on Mars or might even exist today. The reason we cannot say yet that it is definitely life is because we don't understand Mars enough to say that. We don't understand the chemistry of Mars. But let me tell you a bit about what Curiosity found. So carbon, we talked about this wonderful sticky molecule that makes us all up. Carbon can occur in a couple different natural forms. For those of you that know some chemistry, I'm talking about an isotope. And don't worry if you don't know that word. But for those of you that do, an isotope is basically the same atom, but with different numbers of neutrons in the nucleus. And for those of you that don't know the word isotope, there are naturally some lighter and slightly heavier occurring forms of carbon. And life has a preference to use the lighter carbon. It's easier to get it into molecules. It actually works better for chemical reactions. So we actually found that in very, very ancient rocks here on Earth, if you were to take a sample, it's sort of the first evidence of life we have. We can see that there are layers in ancient rocks where this lighter carbon way outbalances both types of carbon. Something is selecting the lighter carbon and depositing it. And the ratio tells you, basically how much life was there. And the higher the ratio is, the more you're sure that it was life that did that. We found a ratio of light carbon to the heavy carbon in this hole that on Earth we would say would be a life sign. And the only thing that we can't say 100% that that's true is because we don't understand the chemistry of Mars well enough. Mars has a very carbon dioxide rich atmosphere. Maybe that made some different sort of chemicals. One idea, it's kind of far fetched, but it is an idea that's proposed, is that as we went around the galaxy with the sun, we orbit the galaxy about once every quarter billion years. We went through a dust cloud. Maybe that dust cloud deposited a higher amount of this light carbon. But at any rate, that hole that you're looking at, that little drill hole that Curiosity made, that might actually have the chemical signals of an ancient, almost fossil of life. So we'll be following up on that. And that was something that happened, like I said, just a couple of weeks ago, we released that. It's very, very intriguing. I'm not exaggerating. I checked with the scientists to say that that amount, that imbalance of light carbon to heavy carbon is marked enough that on Earth we'd say that was a life detection. So of course we have gone back to Mars, and we're going to find out what else is there. And this is a wonderful picture of the Mars Perseverance landing site. The crater that we landed in is about a 60-mile across crater, and it has these wonderful drainage channels. Rivers actually drained into this crater, and the crater was a large lake. And when rivers enter a larger, deeper lake, they deposit material. It's called a river delta. And the idea was to land Mars Perseverance right on this river delta. You can see that there's this wonderful sort of delta of material that's coming out from this river area where the river deposited all of its silt. And this was a really difficult landing. We were landing in much harsher terrain than we ever have. And again, one of the most amazing moments of my life working for NASA. First, I'll say this is an artist's conception of what the crater, Jezero crater, looked like billions of years ago. We believe that this was a lake for quite a long time. And one of the things I love about this site, I mean, even though the lake is obviously dry now and has probably been dry for billions of years, this is an ancient, ancient lake. We believe that this was actually the oldest lake bottom preserved in the solar system. You know, what's it like to have a billion-year-old lake bottom? That's what we're going to actually be looking at with the Perseverance rover. And this is, I love this. I know that many of you have seen this, but this is actual footage from the landing. We have cameras that are looking down at the surface of Mars from the lander, and we have cameras looking up, and they're actually going to see the parachute open as this comes down. So the way that this, both Curiosity and Perseverance landed was there was a parachute that came out. And then after it slowed the descent of the spacecraft for a little while, they cut the parachute, and then it came down on retro rockets and eventually actually lowered the rover down on a little bit of a crane. So you'll hear them talking about things like a sky crane. The sky crane maneuver is actually lowering this delicate rover down on a crane. But this is an amazing real capture from Mars of the landing. So I'll play that.
Meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
Real footage, looking up and down.
Started, about 20 meters off the surface.
And then you'll see them actually cut the rockets and fly away.
Tango Delta.
Touchdown confirmed.
There it goes.
Perseverance safely on the surface of Mars, ready to begin seeking the sands of Tesla.
That blows my mind. That's actually real footage of that spacecraft landing the rover and then flying away. One thing you didn't see in that video, but that came out before, is the parachute. And as I mentioned, this parachute slows it down enough in time for them to actually use those retro rockets. It's an amazing supersonic parachute. And this is real footage again. This is the camera on Mars looking up at the parachute as it lowers the rover down. And all of us looked at that parachute as it was coming out and said, why is there that weird pattern on it? You know, did they run out of red and white stripes? I mean, what's going on? And I have to say, this was one of the most fun things about working at JPL. JPL people, they love Easter eggs. They love putting little messages and things. And it turns out that it was very, very quickly discovered that that was actually a computer binary code. And if you start in the middle of the parachute reading the red and white stripes, if you start from here, it goes dare, D-A-R-E, mighty things. Dare mighty things And the very outer ring is the coordinates, the longitude and latitude of JPL. Dare Mighty Things is the motto of JPL. It actually comes from a quote by Franklin Roosevelt. So far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to take rank with those poor spirits who neither enjoy much nor suffer much, because they live in the great twilight that knows neither victory nor defeat. We know that a lot of the stuff we do is quite risky. Landing something on Mars is never easy. But that wonderful Dare Mighty Things parachute came out, and I just felt my heart fly. That was so much fun. Oh, by the way, the cameras on the spacecraft were not the only things that caught it opening. There's a real picture that was taken by the Mars Reconnaissance Orbiter of the parachute opening and the little spacecraft below it parachuting down. And you can see that we were getting it spot on. It's landing right over Jezero Crater, right along that river delta that's over to the left of the image. So that's a real image of our satellite watching the parachute open. And of course, the nice thing about Perseverance is we actually have a picture of the rover because we had that little helicopter, Ingenuity. Ingenuity flew away, and you can see on the larger image at the very, very top left-hand corner, we've blown it up here. There is Perseverance watching its little helicopter fly away. Okay, so the thing that Mars has I should say the thing that Mars lacks really. We've talked about living with a star and about the solar wind. The problem with Mars is it has a very small mass, and we believe that the interior cooled off a long time ago. The solar wind interacts with planets differently depending on the strength of their magnetic field, among other things. And I want to talk a bit about the active sun. Now, we are just going into another active period of the sun. The sun has a natural 11-year cycle where it gets very active for a while, then it calms down for a while. And we're ramping up now into an active part. In fact, you probably heard on the news that they tried to launch some of those Elon Musk Starlink satellites. And 40 of the satellites, almost all of them, were actually destroyed by a burst of particles from the sun. We call this space weather, solar weather. Now, this is an image of the sun taken by one of our satellites called the Solar Dynamics Observatory. And one of the things that I want you to look at, it's an interesting image of the sun. It doesn't look like the way that we see it, because this image is taken in very, very high energy light, ultraviolet light, and even X-ray light. And so the images, the part that you see that's bright here, to be hot in the UV and in X-rays, this gas has to be in the millions of degrees. The surface of the sun itself here looks kind of dark because it's not really that hot. There was a very active region, and this is a joke, but I got to tell it. The year 2012, so this was July 23rd, 2012, we were looking at a really violent part of the sun there. You can see the bright region that was throwing off a lot of material. And that was something that looked kind of nasty. So we actually had our eye on it. But luckily for us, it actually turned away from us. The sun rotates. The sun on average rotates about once every 29 days. And so these active regions come in and out of our view as the sun rotates. And but what happened, we actually have spacecraft all the way around the solar system. And we had another solar satellite that happened to be looking at this active region. Now, this is from the Stereo mission, which is, there's actually 2 satellites that look at the sun. They are quite far away from Earth. And right now, this particular Stereo satellite was actually kind of behind the sun from where we are. You can see that active region is actually in the view of the Stereo spacecraft. And here's what happened. You're seeing the solar wind there. Those bright streaks are particles coming away from the sun. Okay, there was a little bit of a burp there. Okay, we saw that. But now, blam, there was a huge explosion from the sun. And you'll notice that there's all of this kind of snow-looking stuff in the image of the spacecraft. It basically knocked that spacecraft silly. So there was a huge burst, trillions of tons of high-energy particles thrown out into the solar system. Now, had that hit the Earth, it probably would have brought down our electrical grids. It would have caused a huge problem. It's not dangerous to us biologically. The atmosphere protects us from those high energy particles, but it could have destroyed satellites. It actually could have taken down whole grids and caused blackouts. And so it didn't, the joke that I was going to tell is that it happened on the year 2012. And I had spent the entire year telling everyone that nothing very interesting was happening. Do you remember the Mayan apocalypse 2012? Nothing from space is dangerous. Everything's okay. Yeah, if that thing had hit the Earth, we would have had to eat our words. Nothing to do with the Mayan apocalypse, but just bad luck. The sun is a powerful, active, and changeable thing. We think of it as not changing much, but the solar wind and the stream of particles can be very, very violent at times. And it's the stream of particles from the sun and these sort of violent burps that cause planets to be uninhabitable over time. So this is an artist's conception of probably the thing that saves us most, that most people are not aware of, and that's the Earth's magnetic field. In this animation, there's a blast of high energy particles coming from the sun. And as you can see, the particles are kind of moving around the Earth, kind of avoiding it. And the reason that happens is that we have a core of liquid metal. And as the liquid metal in the outer core of the Earth moves around, it generates a very powerful magnetic field. That magnetic field can actually direct these high energy particles from the sun. And so one of the big things that makes a planet habitable is whether it has a magnetic field. And unfortunately, for our wonderful companion planets, Venus and Mars, neither of these planets have a strong magnetic field. In the case of Mars, the solar wind just blew the atmosphere away. And okay, I mean, for a while, Mars was able to sustain its atmosphere because it has huge volcanoes. This is an image of Mars where you can see the largest volcano in the solar system. This is Olympus Mons. Olympus Mons is more than 60,000 feet high, which is kind of amazing. Whenever I think about, being 30,000 feet up in a jet, that would just be halfway up Olympus Mons. And these are the giant Tharsis volcanoes that you see here. If Mars could still have that volcanic activity, it could replenish some of its atmosphere. But that activity seemed to die away long ago, most likely because the planet's smaller and just didn't retain the internal heat that the Earth has. Our other neighbor, Venus, interestingly enough, the same thing was the problem with Venus. Venus as well, even though it's about the size of Earth, and it's certainly warm. The surface temperature of Venus, the rocks are about 800 degrees Fahrenheit. It doesn't have a strong magnetic field. And then that's a mystery to us. We have some possible ideas why not, but we don't know for sure. This is a picture taken by the latest Japanese mission that went by Venus. And you can see that Venus has a thick, cloudy atmosphere. It's very rare to be able to see down to the surface at all. And that atmosphere is almost all carbon dioxide, famously a greenhouse gas. It keeps heat in. So Venus is very, very good at retaining its heat. Over time, we believe that the solar wind blew away lighter elements, lighter chemicals from the atmosphere like water vapor. And what was left behind was kind of a witch's brew of carbon dioxide, sulfur, all sorts of stuff. And it formed this very thick, heavy atmosphere. So it's a strange thing to think. In the case of Mars, the solar wind blew the atmosphere away. In the case of Venus, Venus has enough gravity, it could hold on to a lot more gas against the solar wind. But the lighter stuff, the stuff that like water, which actually helps clean carbon dioxide out of the atmosphere, maintains a cycle that's good for life. The lighter stuff was blown away, leaving this heavy, kind of poisonous atmosphere behind. Venus is getting to be really increasingly interesting to us. So as I mentioned, Venus and Earth are about the same size. The thing that's really different about them is the rate that they rotate on their axis. The length of our day is 24 hours, where the length of their day is 5,832 hours. It barely rotates at all on its axis. And in fact, it actually takes longer for Venus to make one rotation on its axis than it does for Venus to make 1 year, one trip around the sun. We don't know why Venus isn't rotating. Again, there are many ideas. We don't have an exact idea. But is it possible that this lack of rotation means you didn't get that sort of convection of the metal in the core to generate a magnetic field? We just don't really know yet. We don't understand how planets work. It's an incredible thing to say, but even planets that are similar to the Earth, sometimes we have no idea how they work. These are pictures from the surface of Venus. The only spacecraft that have landed successfully on Venus were from the Soviet Union, the Venera spacecraft. And as I mentioned, the surface of Venus is about 800 degrees. The surface pressure, the air pressure, is equivalent to being about a mile under the ocean. So it's very hot, very high pressure. And we see sort of almost kind of a volcanic looking landscape. We have other ways of studying the surface of Venus. This is actually taken by the Magellan spacecraft, which took a radar image. So through the clouds, it bounced radio waves. And this is actually, let me explain the color of this image. When you bounce radio waves off something, if rock is very nice and smooth, the radio waves reflect very well. And if the rock is really kind of jagged and uneven, then the radio waves will scatter and you won't get as good a reflection. So the lighter areas you see here are actually smoother areas. The darker areas are rougher areas. That's what a radar image tells you. But the cool thing, and the thing that was a mystery when we looked at this radar image of Venus, is that these smooth areas kind of loop around and they may form actually sort of huge lava flows. Now, this may have been an active volcano long ago. There may be active volcanoes still. We just don't really know. But the scale of those lava flows is unbelievable. Lava flows that go around half the planet. Whatever volcanism is like on Earth, and on Venus, it's very different. It's on a much, much bigger scale. Looking a little bit in detail at some of these radar images of Venus, we see these, it looks kind of like a smiley face, but we see these things that are like giant souffles that are in some cases 100 miles across. Big giant magma bubbles that came up, cracked the surface, and then sunk back down. It seems as if almost the entire surface of Venus becomes sort of a bubbling mass of magma periodically. The surface doesn't have many craters on it. So right now, as far as we know, none of this is going on. All of this is extinct. But we are wondering if there may be some volcanism that's still active. Is there some natural cycle of Venus where the energy kind of gets trapped inside, and every hundreds of millions of years, the whole planet becomes a big super volcano? All of these things are questions that are waiting for us. This is another radar image, in this case black and white, of this relatively weird, cracked terrain where big magma bubbles bubbled up and sunk back down long ago. It also has things like Maxwell Mount. This is an image from one of our spacecraft of the highest mountain on Venus at over 38,000 feet high. We're not even sure how Venus made a mountain that high. I mean, the similarly high mountains are due to things like the Himalayas being pushed up by our plate tectonics. So this is a very, very odd place, and this planet does not work the way that the Earth does. By the way, just a little note about Maxwell Mount. There's some different coloration that you see up here on the ends of the mountain, and we actually believe that this is a kind of snow. But the atmosphere is so hot on Venus that this is actually a metallic snow, probably lead and bismuth. Lead snow. So the gases get so hot, then they go over this mountain and they get cooler, and what actually comes out of them, what precipitates out, is metal. This is a little vacation shot. We mentioned the amazing the amazing ALMA observatory, which is at nearly 17,000 feet. That's the highest I've been. ALMA had a very amazing result about Venus recently. So the surface of Venus is pretty hell-like, very, very dry, no water, very hot, not a great place for life. But there are areas up in the clouds of Venus where the temperatures are not so bad, and the clouds are actually quite dense. And ALMA was able to detect a very, very interesting feature in the clouds of Venus, and that was the chemical signal from an element called phosphine. Phosphine on Earth is a life marker. It's something that bacteria can produce. Interestingly enough, it's something that even bacteria that are at high altitude in our atmosphere, there are bacteria all over the Earth, including very high in our atmosphere. Is it possible that there was once life on Venus, maybe life on the surface? High altitude bacteria got into the clouds. Then over time, the surface died away, becoming too hot for life, but the high altitude bacteria are still there. Nobody considered Venus to be a good candidate for life until we found that phosphine. And so now we have two missions that were selected by NASA this year to go and investigate more. These missions will be working in conjunction with each other. The one on the left is called Veritas, which is led by JPL, and the one on the right is called Da Vinci, led by Goddard. Veritas will be scanning the entire surface of Venus, looking for activity, volcanism, get more of a sense of its geologic history. And Da Vinci will actually be a lander that plunges down, parachutes down through the clouds of Venus. And there's a specific instrument on there to look for this phosphine, to look for the signal, to see if there's any more evidence that this might be produced by bacteria. Once again, this is another signal that when you see phosphine on Earth, you say, aha, life. We can't say that yet for Venus because we don't understand enough about the chemistry of Venus to be that sure. Now, this is something that I promised you, something that's hot off the presses. This is actually an image taken just a few weeks ago, released today And it's the Parker Solar Probe, which I'm going to talk about in a second, that's going to be exploring this solar wind of the sun. The image on the left is a visible light image of Venus taken by the probe. And what I want to show you, this blew our minds. The probe was actually on the night side of Venus. It was looking down at the dark side away from the sun. And at first we thought that we were just seeing clouds. Everybody knows Venus has clouds. And then we realized that the colors, the shapes, exactly corresponded to the landforms that were underneath there at that time. This is actually a high plateau called Aphrodite Terra. It's something that on Earth would be a continent, something that would stick up above the oceans if there were oceans on Venus. This higher altitude area is actually a little bit cooler, and that's why it appears darker here. Now, this is invisible light. The rocks on Venus are so hot at 800 degrees, they're actually glowing red hot, faintly, but they are glowing red hot. And the higher altitude rocks sticking up a little bit above the surface are a little bit cooler, so they're a little bit darker. But that blows my mind. If you were on the night side of Venus, you would see a faint red glow underneath from the planet below. I mean, that's amazing, and an amazing new image from Parker. Okay, so Parker Solar Probe, and we're going to end with talking a little bit about the solar wind. Parker is looking at the origin of these particles that actually can make a planet habitable or not, can blow away an atmosphere or make it a chemical brew. What's it doing around Venus? Parker is orbiting the sun right now. And the amazing thing is that it's going incredibly fast. It's on an orbit sort of like a comet. It goes in towards the sun and then goes out again. And when it goes in towards the sun, it goes around very fast. It's actually traveling at nearly 400,000 miles an hour. That's incredible. When I first started talking about Parker, I had to look that up to make sure I was right. When it goes close to the sun, it's traveling close to 400,000 miles an hour. But Venus is doing something for it. Venus is allowing us to get closer and closer to the sun. And you may not really understand why. When you launch something from Earth, it would seem like the easiest thing in the world. Just throw it out into space and the gravity of the sun will suck it in. But that's not what happens. That's a good thing because that would happen to the Earth if that were true. So this is a little video about why it's hard to get the Parker Solar Probe close to the sun and what Venus has to do with it.
NASA's Parker Solar Probe will soon fly closer to the sun than any spacecraft before it, about 4 million miles from the visible surface. But getting that close to the sun requires some fancy orbital mechanics. It takes 55 times more energy to go to the sun than it does to go to Mars. Why is it so hard to get to the sun? The answer is related to why Earth doesn't just fall straight into the sun, despite the strong gravitational attraction. Earth, and everything on it, is traveling very fast, about 67,000 miles per hour, in a direction that is basically always sideways relative to the sun. If you launch a rocket from Earth straight toward the sun, it won't lose that sideways speed, and so it will miss the sun. The only way to get the rocket to go right into the sun is to cancel all that sideways motion. Leave even a little bit, and it will miss the sun and enter a new orbit. To cancel Earth's motion, you have to launch the spacecraft backward as fast as Earth is hurtling forward. But 67,000 miles an hour is really fast. Spacecraft have to go upward at only 25,000 miles an hour to escape Earth. Getting to Mars only requires a bit more speed, 29,000 miles an hour. New Horizons, which NASA sent rushing out to Pluto, managed 36,000 miles per hour, or a little more than half what it would have to do to hit the sun instead. Since Parker Solar Probe plans to fly past the sun, it doesn't need to cancel out all of Earth's sideways speed, but it does need to remove 53,000 miles per hour of it. That's why it's using one of the most powerful rockets available, and additional gravity assists from Venus over a period of several years. In this case, rather than speeding up the spacecraft, as in a typical gravity assist, Venus slows down its sideways motion, so the spacecraft can get close to the sun. When it finally does make its closest approach to the sun, Parker Solar Probe will have lost much of its sideways speed, but gained a great deal of overall speed thanks to the sun's gravity. Parker Solar Probe will hurtle past the sun at 430,000 miles an hour, the very first human-made object to get that close.
It's a wonderful thing to think of. It's a wonderful thing to think of that's actually one of the reasons that we're using Venus is to slow us down. Usually we use a planet like Jupiter or Saturn to slingshot us out of the solar system. But in this case, we're doing the opposite. It's a gravity assist, but it's actually slowing us down instead of speeding us up. And that allows us to get rid of the natural orbital motion of the Earth so we can go farther and farther in and closer to the sun. So kind of wrapping up the idea of habitability, there are so many things that turn out to actually determine whether a planet can keep its life or not. Things like plate tectonics. Venus doesn't have them, Mars doesn't have them. Plate tectonics are a function of our active core. They also regulate the temperature of the planet. We're really, all of these things we never thought of before, that these things are really what keeps our planet alive. One of the things that's happened recently is that we've understand that the Earth itself's climate naturally changes a lot. We now have evidence that the Earth went through a couple different phases called snowball phases in its history. So what happened in a snowball phase is that we believe this was an influence of the first life on Earth. And it's amazing to think that life has been affecting the large climate of the Earth for a long time. But life and geology, life and the actual structure of our planet have been intimately involved since life arose. I mean, some of my favorite things, I've got a piece of tiger iron, and you can see these in a lot of museums, but this is a piece of basically iron, and it comes from a time so long ago that there was not much oxygen in the atmosphere. The very first life, plant life, single-celled organisms, microbial life, began to release oxygen as a waste gas. And so there are layers in this iron that are reddened because they were rusted by that release of oxygen. Then all that oxygen basically was oxidized. It was used to rust rocks. And so for a while, there wasn't much oxygen anymore, and the iron is sort of gray colored. But then more oxygen gets released and more, until finally, all of the iron on the surface of the Earth was rusted, was oxidized. So the very structure of our rocks changed when life began to release oxygen into the atmosphere. I think that on a lot of planets around other stars, we're going to find life, but maybe a very simple life, maybe the sort of microbial single cell life. And we know that that exists on Earth too. I was showing this to Andy before. It's actually kind of dangerous, but I have in my geology collection something called a stromatolite. And a stromatolite is a fossilized colony of bacteria. And this is what we look like for about the first 2 billion years of life. Not much happened. Basically, blue-green algae and bacteria were very successful and very common. And that's pretty much how it stayed for billions of years. But then what happened? Well, think about plant life. Plant life releases oxygen, but it breathes in carbon dioxide. There was enough plant life, enough algae, enough bacteria to actually breathe in enough carbon dioxide that the natural greenhouse warming layer of our atmosphere was destroyed. And the Earth froze. And we think that it did this twice, and each era lasted at least 10 million years. This is an artist's conception of what we think the Earth might have looked like during one of those snowball phases. There probably was some open water by the equator, but there may have been glaciation pretty much over the entire planet. What this did is that this actually gave evolution a punch. Life was constrained, it was put under stress. Little bits of microbial life were frozen together in little inclusions of water. That set off the explosion of evolution that we call the Cambrian explosion. We think that happened after one of these snowball episodes. So do you need to have a climate that's stable but not too stable to actually punch life and get evolution going? So many things about what makes a planet habitable and what may actually make it suitable for complex life like us. This is actually a simulation we ran at NASA trying to figure out how much water could have been open during that time when most of the Earth was frozen. So at NASA, we're actually working on computer simulations of how this climate might have worked and what the snowball Earth would have been like. It's not something that we think of, but Earth for a long time might have looked something like Europa for 10 million years. So putting this all together, when we look at planets around other stars, how will we know if they're habitable or not? This is an animation of a system that I would never have believed existed if I hadn't seen the data myself. And that's the TRAPPIST-1 system. Around TRAPPIST-1, we know of 7. There may be more planets farther out, but there are 7 Earth-sized planets that are very, very close in. And we can see them because they pass in front of the star. And when they pass in front of the star, they block out a little light. So all these little blips in the data you see, this is sort of the light level of the star. And then when one of these little planets goes in front, the light dips. And we see that over and over again. These 7 planets are actually in a space that's not much larger. It's about twice the diameter of the inner moons of Jupiter. You know, the Jupiter out to the moon Callisto. Tiny, tiny little solar system around a star that's very dim, a red dwarf star. So if you snuggle up close to a dim star, you might have the right temperature for something to be Earth-like, and maybe even have liquid water. This is an artist's conception of the TRAPPIST planets. And we don't know what their surfaces are like, but as you can tell, the artists are wondering if some of these might actually have liquid water on them. The ones that are closer to the star are probably a bit too hot. The ones that are farther out a bit too cold. But there may be 3 or 4 planets of these Earth-sized planets that could be habitable. But now the question is, what are they like? Do they have magnetic fields? This dim star, it's called an M-dwarf star. M-dwarf stars have been known to put out huge solar flares. So they may be bathed in an intense solar wind. One of the things that we're going to be doing with the James Webb Space Telescope is, for the first time, we're going to be able to actually measure what the atmospheres of planets around other stars are like. We have instruments that can actually tell us how dense the atmosphere, what the temperature of it is, whether it has things like water vapor, methane, carbon dioxide. So the incredible thing is that with the launch of the James Webb Telescope, and the TRAPPIST system is definitely one of the targets it's going to be looking at, we're finally going to be able to know, at least atmosphere-wise, whether these have an Earth-like atmosphere and really may be habitable. So all the way from our own solar system, all of the factors that make a planet habitable, the star, the geology, the plate tectonics, the evolution of life. Now we're going to be applying that to look at actually planets around other stars and try to piece together their stories too. And I'm really looking forward to that. As I mentioned, the first light is now passing through Webb's instrument. We're focusing the mirrors right now, and we're hoping to have some of our first images out in late April or early May. And if you invite me back here in a year, I may be able to say one of these planets has an atmosphere very much like the Earth's. I hope that turns out to be true. So thank you.
Well, thank you so much. What an amazing tour of our history. David, is it okay?
I was just sharing. Yep, all good.
Okay, great. So thank you for that remarkable tour of our history and the potential of looking at other worlds. What we're going to do now is to hear from our viewers and to see what kind of questions they've sent in. Before I turn things over, I just want to say thank you, not only for your talk, but for all those remarkable visuals. I loved the little animations and tours. That was great. Let me now introduce Dr. Jeff Matthews, who is the astronomy professor at Foothill College, and he's going to be curating the questions for Dr. Thaler. Jeff, why don't you take it away?
All right. Well, thank you, Andy. And again, I'd like to repeat, thank you to Dr. Thaler for coming out and speaking with us this evening. We've got a lot of questions that have come in, so I'm going to apologize right up front. There's no way we're going to be able to get through all of them. So I'm trying to lump them together. There've been some similarities to them. So we'll start off with a question from Allison, asking you to elaborate on, you said something about the meteorite sample being more complex in its makeup than humans. So just a request for a little elaboration. Any elaboration you could add to that?
It's an amazing question. And this is actually one of the ways that we search for life on a place like Mars, too. So it turns out that life actually only uses a small subset of the organic molecules that rain down on us. So one of the biggest things that life does is that you may have heard of something called handedness or chirality. So in organic molecules, the reason it's called handedness is that organic molecules, these carbon-based molecules, can basically occur in sort of mirror images of each other, like our hands are mirror images of each other. And for some reason, molecules occur in both of these formations, but life only uses the left-handed. So right off the bat, there's like half of the organic molecules that are not used in life. And this is a mystery as to why life chose that. whether it was random, whether it had something to do with our environment in space. Some people suggest that we might have, in the very early part of the Earth, we might have been close to a strong magnetic field, like a neutron star. And maybe that actually kind of polarized things. Only one part of the molecules got through. So meteorites have both right-handed and left-handed molecules. First thing, life only uses half of them, and we don't know why. But even fewer than that, actually. I mean, of the molecules that are left-handed that it uses, there are more molecules, more different kinds of molecules in a meteorite sample like this than my body uses. Life only uses a small sampling that's available. And in fact, one of the ways that the Curiosity rover or some of the other rovers on Mars might find life is if they're drilling through a rock sample and there's lots and lots of different organic molecules, then there are fewer types of organic molecules. That could mean it's processed by life. In meteorites like this, there are nucleobases. Nucleobases are the type of things that make up our DNA. There are nucleobases that we don't use on Earth. No life uses them that we're aware of. And one of the really interesting questions is if life on Mars used a totally different nucleobase structure, would we even recognize it? Would it be something chemically that we wouldn't even look for? So we have people in our laboratories at NASA that are grinding up meteorites to find these molecules that are there, but our life doesn't use. We don't really know why, but it doesn't. And is it possible that there are ways of making different kinds of DNA, different sorts of information-bearing molecules out of these different nucleobases? So yes, there are more different kinds of organic molecules in meteorites than life on Earth uses.
Wow. And okay, I'm going to add my own question in. I'm going to cheat and throw my own question in here real quick. Is anybody doing experiments to see like, hey, can we make novel biological molecules using some of those unused bases?
Yes, I mean, so the paper uses the term informational polymers. So DNA is a polymer, and it can carry genetic information. And so yeah, they're looking at some of these different nucleobases and seeing whether it's possible to form different kinds of informational polymers. Yeah. So I mean, one of the things that I think will be really wonderful is we've flown through the plumes of water coming out of some of the icy moons in the outer solar system. So the moon Europa on Jupiter and the moon Enceladus around Saturn, they have liquid water oceans that actually vent through cracks. And in the case of the Cassini mission, which flew around Enceladus, there were organic molecules flying out, with that water. And we really want to go back and see what was there. And so, is it possible to identify an informational polymer that's based on different nucleobases? There are people at NASA working on that. So we have an entire department, and Ames too, actually. Ames Research Center is a big center of the astrobiology. Astrobiology has got to be the coolest topic. It's just wonderful.
Wow, cool. Okay, so we got a question here from Ed asking about the solar wind. And so you mentioned that it can strip a planet of its atmosphere. And so he mentions that the Earth's magnetic field reverses over geologic timescales. And does that present any danger of the Earth's atmosphere being affected by the solar wind during times when our magnetic field is a little weak?
Yeah, I mean, it's something that we don't know much about. Yes, the Earth's magnetic field does naturally reverse. The thing that we have not been able to correlate that with is any huge extinction. I mean, it does not appear to be like a global extinction time. It very well may affect like migratory birds, for example, could be thrown off if the magnetic field is chaotic for a while. I mean, I can well imagine that when the Earth's magnetic field, when we believe that when it switches, it's not so much that it disappears, but it becomes a lot badly organized, and then eventually it kind of organizes again in the opposite way. We certainly could lose more atmosphere than we usually do to the solar wind. We lose some atmosphere to the solar wind all the time, but our atmosphere is also replenished by things like volcanism and other processes. So it's possible that we'll lose a bit more, but I would think that the rate won't go up hugely. The Earth has also strong gravity that can keep its atmosphere down. But I have to give you a little bit of a cautionary tale from space. I mean, there are these very violent exploding stars that we call gamma ray bursts, and they're relatively rare in the universe. I mean, let me define rare. We have satellites that detect about one a day. but that's all over the sky, most of them in very, very distant galaxies. There was a gamma ray burst that came from a neutron star that's about 50,000 light years away from us. And it blew off a measurable amount of our atmosphere when that came by. So, it actually, it blew off the top of our atmosphere, a bit of it, enough for us to notice. And it actually sent our whole magnetic field kind of ringing like a bell. So, I mean, there are nearby energetic phenomena that are almost sort of like a super duper solar wind that when they hit us can blow stuff off. So yeah, that happens to the Earth. And it may be that during a switch over the magnetic field, the rate increases, we lose a little more, but I don't think it's really significant. That's my guess.
And you said that was 50,000 light years away?
50,000 light years away, yeah. Something 50,000 light years away blew off a noticeable amount of our atmosphere, yeah.
I love the astronomical definition of nearby. So I've got
In
a
our
question
galaxy.
here.
Yeah.
So I've got a question from Nulai asking, why does the mission returning material from the asteroid take so long to get the sample back to Earth?
Oh, hey, I mean, when we took it, it was like 200 million miles away. I mean, that's pretty good. So the reason basically is that you have to wait for things to line up properly. So Bennu is one of what we call the near-Earth asteroids. Its path actually does cross the path of the Earth, and it goes around the sun with a period. I think it's a little bit more than a year, but it's actually similar to the Earth's orbit. And it comes close to the Earth at some times, and then at other times we're sort of on the other side of the sun from each other. So it's sort of the same thing about, you've got two objects that are both orbiting the sun independently. Sometimes they're quite close, and sometimes they're on the other side of the sun. And so, we have to wait for Bennu to get closer to Earth, and then we'll pop off and actually have the little spacecraft come back. So it's a question of waiting for the orbits to line up. It's always one of the things that, when we talk about sending people to Mars, one of the biggest challenges is the time they have to be there. They can't just come right back, because sometimes the Earth and Mars are on the same side of the sun, pretty close to each other, and sometimes they're on the opposite side of the sun. So you need to wait. You need to wait for them to be in the right configuration to go backwards and forwards. And that's the same with the Earth and Bennu.
Okay, so then switching to some questions about JWST, I've got a question from BJ asking, can and will JWST look for Planet X?
Yes. So it depends on how you say look for. So for those of you that don't know, Planet X is a possible, a hypothetical large planet in the outer solar system. Unlike people often ask me, is this planet Nibiru and stuff? It's something completely different. It's something very, very far away, something that never comes very close to the Earth at all. And the evidence we have for it is that the orbits of some of these smaller bodies like Pluto and other objects like Pluto out there that we call the Kuiper Belt objects, the orbits appear to be lined up in a very interesting way that really doesn't seem to be able to be just pure chance. It's almost as if something larger comes in closer every now and then and actually kind of herds these smaller objects into these orbits. And there are some estimates that this could be larger than the Earth, that this could be a planet that's maybe anywhere from 5 to 7 times the mass of the Earth. The unfortunate thing is it's not been detected yet. All we have is this indirect evidence of the orbits of these smaller bodies all lining up. And if this is in a very, very long, almost comet-like orbit that goes way into the outer solar system, if it's in its outer part of the orbit, we may not be able to see it. But there are surveys of the sky, usually surveys in the infrared, that are looking very hard for this, because these lined up orbits are enough of a clue that it really, really could be real, and that would be spectacular. And remember, we were talking about how we think in the early solar system, the giant planets started tugging on everything, and they started throwing everything around, and that's maybe how water got into the inner solar system. It's possible that tugging actually threw other planets out into big, long orbits. And so if Planet X is out there, it may have been thrown out there at the time when the giant planets were jockeying around and sort of hitting, sort of gravitationally pulling everything around. If we identify anything that on the survey looks like it's about the right object, but we can't really see what's out there, The James Webb Space Telescope will aim and try to see what it can. The James Webb Space Telescope will be doing surveys of the Kuiper Belt objects. It'll be able to take amazing images of the closer by planets, basically anything farther away than the Earth, because famously there's a heat shield that always has to point towards the sun, so it has to look out from the sun. So it's not going to look in to see Mercury or Venus. That would be bad. But anything farther away from the Earth, Mars and out, we're going to have some incredible images of. And so yes, if we can identify on one of these all-sky surveys something that looks like it might be planet X, Webb will definitely have a look at that. Yeah.
And if there is such a planet that gets found, what might be the prospects for life on such a far-out world?
Well, it's funny. I couldn't tell you, because one thing that surprised the heck out of me was Pluto. Pluto is a small body, and it shouldn't have like really any internal heat or anything like that. When we got out there, there's substantial evidence that there's liquid water under the ice of Pluto. And nobody really understands why or how. And Pluto also has naturally occurring organic molecules on it. Pluto's actually very influenced by the solar wind. Pluto actually loses hundreds of tons of atmosphere a day due to the solar wind. And as the solar wind hits some of the methane in the atmosphere, it causes tholins, these organic molecules, to be created. So you've got organics and you've got liquid water on Pluto. So I think it's perhaps a less likely place for life, but I wouldn't say it's impossible, because these outer worlds are far more active and far more interesting than we expected. And I mean, I think that was to me the real benefit of New Horizons. I mean, I'll admit, I was one of those people when they said, "Oh, we want to just photograph Pluto, just fly right by it." I was like, "Really? Is that worth the money to do that?" But when we saw Pluto and it had active glaciers and evidence of a huge reservoir of water, it changed the way we realized we don't know how these outer planets work. We don't know what the heat source is, but it has one. So who knows?
The universe is being more creative than we gave it credit for.
No one expected that. We thought we could see a dead little icy rock. That was it. It was anything but.
So we're going to come up here soon on the end of the question. So I guess we'll just do a couple more questions from those that have come in. So we have a question from Steve asking, could the space probes that landed on the surface of Venus have accidentally taken microbes from Earth that could survive and thrive?
Yes. So this was actually why we didn't land on the moons. So, I mean, to give you a little bit of a context, Cassini was the mission that went out to Saturn. Oh, I'm sorry, you're talking about Venus. So life is very, very tenacious. And we know of bacteria that can exist in the hot pools of places like Yellowstone, very high acid levels, very high temperatures. The clouds that we're looking for these bacteria in have very high acid levels. So we will be looking for basically an extremophile, some sort of bacteria that can handle more acid than we normally do. But the actual surface of Venus, I'm betting, is pretty darn dead. Not only is it 800 degrees, but it's very, very dry. All of the water has been baked out of those rocks. And so, Venus is hugely dry. And so I think for those two reasons, I have my doubts that microbes would survive for any amount of time on Venus. They're pretty much every other place we land, we are quite worried about that. A lot of the more interesting places on Mars, we don't land because we worry about contaminating possible groundwater. Cassini, we actually threw into the planet Saturn because we didn't want it to accidentally hit Enceladus or Titan, possibility of life there. But there's always a risk whenever we explore. There's no way we can get rid of all the bacteria. I mean, we've learned that. We can sterilize things, we can minimize the risk, but there's some bug that's going to survive almost anything. So my guess is that Venus is pretty safe on the surface for that.
All right, and so here we'll have our final question for the evening. And this is a question actually about the idea of terraforming. And so you talked about how life had affected Earth in the past. Is there a way that human life could? We've had several people actually asking questions about terraforming. Is there a way that human life could go on to affect, say, Mars or Venus? And
Yeah. I guess the whole question of terraforming, to me, I mean, the scale of it is something that I find very hard to imagine. And there certainly could be ways. Well, for example, let's talk about the natural evolution of the solar system for a second. I mean, we mentioned that planets lose their habitability after a while, and the sun is naturally becoming hotter and brighter as it ages. And again, let me be very clear: this is not human-based global warming. Human-based global warming is increasing so fast that if that were a natural cycle, we're about to die. So I mean, it's not that, but over hundreds of millions of years, probably in the next 200 to 300 million years, the sun will increase its brightness and its temperature enough that the Earth's water will largely boil away. So that's the sort of the end of the habitability, at least for large scale life on the surface of the Earth. And 200 million years sounds like a long time, and of course it is, but it's a little sad that when you think about, we've had life for over 4 billion years. We're near the end of the life cycle of Earth. So is there somewhere else where we can go? Well, as the sun becomes hotter and brighter, it could very well warm Mars significantly. And if that happens, melt the ice caps, melt the permafrost, the frozen water, with human help, could you actually, sort of keep introducing gases into the atmosphere? I mean, even if you had no magnetic field, and I don't know how you would generate a fake magnetic field over a planet. I mean, maybe locally, but not over a whole planet. Even if the sun was blowing away, as long as you were introducing enough of that every day that you were adding more atmosphere that was blowing away, then you could conceivably change it into a more Earth-like environment. The scale of that, though, I can't imagine having enough gas factories all over Mars to do that. The other interesting thing is when the sun gets brighter and hotter, what happens to the moons of the outer solar system? What happens to worlds like Titan? Titan looks very much like a primitive Earth in terms of its atmosphere. Titan, I mean, for those of you that want to do a little reading, has another instance of what I think is a possible biomarker. Not me, NASA thinks is a possible biomarker. When we sent a probe down through the clouds of Titan, it was called the Huygens probe, there were certain gases that were out of balance. And intriguingly, they were the gases that methane-based bacteria use here on Earth. And you have lakes of methane on Titan. So that's always got me. We're sending, by the way, we're building right now the Dragonfly mission. And the Dragonfly mission is a car-sized drone that's going to fly, an octocopter that we're sending to Titan. I can't wait. I mean, we would better have a video camera on that. That's all I'm saying. But that's going to be actually looking around some of the environment of Titan and trying to understand the chemistry, because it was so cool that like the things that are out of balance on Titan are the things that methane-based bacteria use here. That's really neat. It's possible that as the sun warms, those worlds will become more habitable. I mean, maybe habitability will move out into the outer solar system as the sun gets hotter. And remember to send it the opposite way too. So in the past, the sun was cooler and dimmer. And that's when Venus was probably, more likely to have conditions like Earth. So, Venus may have been the first habitable planet. Life may have started there, and maybe some of the bacteria are still in the atmosphere. So you're looking at sort of a cycle of life going out through the solar system, starting with Venus, Earth, Mars. Mars was a problem because of the no magnetic field, and maybe it goes out even further. Yeah.
Well, thank you so much. What a lot of thoughts we're going away with from this talk. It's very rare that you can actually say that you've heard an evening lecture that has told you a lot about the meaning of life, but yours did. So thank you so much. For everyone, please join us again on March 9th, when Dr. Adam Burgasser of the University of California in San Diego is going to be speaking about the invisible universe of brown dwarfs, these failed stars that are more and more common as we observe the universe. Again, let's thank Dr. Thaler, and we'll see all of you at another Silicon Valley astronomy lecture.